So I got this old physics problem, and it's really wonderful problem. There's a sphere, see? And the sphere has a moment of inertia of 2/5 mr squared, so I guess it's a solid sphere, right? That's what they do. It's got a mass of 25 kilograms, got a radius of 0.2 meters. This is a dense little sucker, maybe it's made out of metal, and it's gonna be rolling up this ramp right here. And it says that it rolls up the incline without slipping, and it also says that it's not going to change its velocity while it's going along here. So I'm going to draw little bumpies to show that there's friction all along this section right here. But remember, it's always static friction, so it's not going to be slowing down here. And when it's going up the ramp, it's not going to be losing kinetic energy to heat. It's only going to be losing kinetic energy to potential energy. So let's start doing this problem. The first part, it says, what is the total kinetic energy of the sphere as it rolls along the horizontal surface? So I'm just going to note that there are two forms of kinetic energy. I'm going to say we've got ourselves K translational and we've got ourselves K rotational. And those take the two forms 1/2 mv squared plus 1/2 I omega squared. It is rolling without slipping, so we can further develop this by saying, I'm just going to write the 1/2 mv squared again. But then I note that omega, by the way, omega is v divided by r. This is true when we have rolling without slipping situation, and we've totally got that here. So I'm going to plug that into there, and I've got, oh shoot, why don't I take this moment of inertia and plug it into there also? Here I go, 1/2 2/5 m r squared, oh, capital R, lowercase r, well, let's just use a capital R right there. And then instead of omega squared, I'm gonna write v squared over r squared. Some stuff cancels. And on the next line, r squared, so, oh, this is so cool. Look, it says 1/2 mv squared plus 1/2 mv squared multiplied by 2/5. That's pretty awesome. What if I just factor out the 1/2 mv squared and say 1 plus 2/5? This is a form that my students in class have seen pretty often, and it helps you to find out the fraction of the energy that is translational and the fraction of the energy that is rotational. That's cool. So 2/7 of the total energy is rotational, and the other 5/7 must be translational. So that's cool. If you actually plug in the numbers right here, you find that this is 1,250 joules plus 500 J's. Okay, cool. So, all right, great. Then the next part of the problem says, what is the speed of the sphere as it leaves the top? And I had people do this in all sorts of crazy ways, but I'm gonna ask you to approach this, by thinking about what's true at the end. That's pretty lame instruction, right? What is true at the end? Well, at the end, the sphere is up here and it has gained potential energy and it has lost kinetic energy. So I'm thinking that mi is mf. If I say that initial mechanical energy is final mechanical energy, then I could write down all the forms of energy that are present initially. Initially, I've got, we just did that, 1,750 joules. And that's kinetic rotational and kinetic translational. Now, what about the final the final mechanical energy? Well, it's got mgh, and the h is 3 meters up. Most of my students stopped right there, and then they said, wait, this is that whole form, the 1/2 mv squared times in parentheses 1 plus 2/5, and then they solved it for v. That's a disaster, because this is not the final energy. If you don't write any kinetic energy term right here, then you're already telling me that you think it's stopped. And you're gonna answer this question with equals 0. Duh, I already know without doing physics. So don't do that, because when you turn that to the side, it looks like somebody doesn't have any idea what's going on. And me, I get angry when that happens. Big pointy teeth. All right, good, that's me. Good, wow. All right, that's a little bit too far. I'm gonna add on 1/2 mv final squared, and we are just going to solve for v final. So wait a second. If it's moving, it's also gonna have to have rotational energy. So I'd better add on here plus 1/2 times 2/5 times m times v final square. And now I have to solve it for v final. Why is that guy in the way there? Dang it. I'm trying to find v final. So I take 1750 joules and I subtract mgh, and that turns out to be really elegantly wonderful. And then I take 1/2 mv final square and I multiply it by 1 plus 2/5 like we've been doing all day long. And I'm trying to solve for v final, so I guess it'll look something like this. It'll be, what are we gonna do? Multiply by a factor of 2. I've got 2 times 1750 joules minus mgh. Oh my goodness. And then I'm supposed to divide by mass, and I'm also gonna divide by 7/5. Dividing by 7/5 is not as good as multiplying by 5/7, but it's too late. The damage is already done. And then I have to screw both sides, and then we're done. Super. So you get some answer, and then, well, I gotta warn you about this next part. It's kind of lengthy, and it's a community project, so get ready. Bye-bye. I'm gonna have to edit all this out. As we continue the problem that you already know everything about, I have a live studio audience before me at this time. Would you say hi, studio audience?
Hi.
Hi. I said hi.
Oh, yeah, sure, okay. So we're on part B, number 2, and we want to know the direction of the sphere's velocity just as it leaves the top of the incline. So I'll give you a little picture. It was shocking to me, the answers that I got on this problem. Are you laughing at the possibilities of all the wrong things that a person could say? There's a ball here, and it's rolling, and it's going to leave the top, and believe it or not, some people wrote things like this for the direction of the ball's velocity. And other people said it will be straight down, and other people, still others, said that it will be that direction. What the heck?
Because sometimes you draw the arrow on the board and it doesn't make any sense.
And you never asked me?
No, you explain it. I mean, I don't know. It's like...
For velocity?
It just seems really arbitrary.
Or for force?
I don't know.
That could be the
I think
confusion.
acceleration.
It's probably for acceleration. The acceleration of the ball after it leaves the ramp? Straight down. Absolutely. But which way is the ball going as it leaves the ramp?
That way.
It's going the way it was going, right?
Right.
It's going to keep doing what it was doing because it has inertia. So if I get out the brown right here, I would go like that. That is the direction. In fact, they're giving us this angle as 25 degrees. And if I were to be really fancy, I would say that is 25 degrees up. Ben, did you get that?
Yeah.
Awesome. Awesome. Should we do part C?
Yes.
Let's just go ahead and do it, unless you have further questions about which way the ball was going. Okay, great. Neglecting air resistance, it says. Neglecting air resistance, ooh, that's fun. Calculate the horizontal distance from the point where the sphere leaves the incline to the point where the sphere strikes the level surface. So now I have a kinematics problem. This thing is going to go, whee, and hit the ground somewhere over there, right? In a parabola. Yep. And I'm trying to find this distance here, that distance to that point over there. I guess I should draw another sketch. So we know how fast the ball's going, as we found in part B1. B1 told us that the final velocity was what? 7 point what something?
7.61.
7.61 meters per second or thereabouts. And we know that the direction, actually I'm going to call that V0 for the launch. Right? Even though it's the final velocity at the top of the hill, it's the initial velocity for the launch coming off of the hill. Now we have a ball that's shooting out in some kinematics-y fashion. It's being launched above the ground. Oh snap, this is 3 meters right here. And it has an initial velocity. What do you think we can do to crack this problem? This is a ball at the top of that hill going that direction, and it will form this parabolic path and land over here. That's going to be delta x. How are we going to find delta x? Go.
Tail of 2 squares.
Tail of 2 squares. A fine idea. In the x direction or in the y direction?
X.
Tail of 2 squares says the final velocity in the x direction square is the initial velocity in the x direction square plus 2 times the acceleration in the x direction times delta x. What's the acceleration in the x direction?
9, or 0.
Good work. So this will go away, and we will find that the square of the velocity in the x direction beforehand is the square of the x velocity in the direction afterwards, but everybody knows that.
So you use it in the y direction.
You're gonna use the y direction? Awesome. In the y direction, you wanna use the tail of two squares?
I don't know. Someone else answer.
There's a good bit of anonymity here because there are 9 of you or something. It's not 9, it's smaller than 9.
You mean 200.
Yeah, there are approximately 200 students gathered around. Hey, what are we gonna do? You wanna try breaking the problem into a part? Like what you could tell me beforehand? What could you tell me?
You know the distance in the y direction.
Distance in the y direction. What? From where? Oh, you're saying I know delta y?
Yep.
That's super important. Delta y equals -3 meters. What else?
It's like square root 2 GH something. I can't remember.
The heck? Where'd they come
What
from?
I'm talking about? I can't remember. That was bothering me the entire time.
All right, we need kinematics equations. The key to solving kinematics problems is what? This is a class 2 problem, which means it's middle of the road, launched at an angle, it's up above a cliff, and we're able to do it. But we want to break it into 2 parts. Where do you know anything?
The beginning
Do we
and
want
the end.
time?
The beginning and the end. The end you know nothing except position, and the beginning you know position and velocity. So that's
Oh,
cool.
don't you do
And we
that?
absolutely do want time. Where do we know something special?
Isn't v naught in the y direction 0?
V naught in the y direction is not 0, because I'm going to have to resolve this sucker. The initial velocity vector is going to be resolved, so I'm
Oh,
going to have
that's if it's going
7.6. Yeah, that would be a class 1 problem. Okay, can you find those 2 components for me? This is 25 degrees right there. I'm totally not going to do that. But what? I'm still looking for when you think you know something special about this.
Alright.
For those of you watching at home, it has been a long time since these particular students were asked to do a problem like this. It appears that it has dropped off of their radar, these special skills they once had.
What was the question?
The question is this: when do you know anything that's going to help you solve this problem?
You know acceleration?
Acceleration in the y direction. Negative 9.81 meters per second squared. Do we know anything else?
Don't you always know that?
We always know that. When we did this problem, we broke it into 2 parts. How did we slice it? Oh, you guys. There is a magic moment.
In the middle?
In the... What? Right here? In the middle? You there! In the back! Do you have any insights about when we know stuff?
At the peak of this thing?
Yeah, totally.
That's what I meant.
That's what the middle
It's not what you said. Okay, so here, what do we know there at that moment?
Acceleration 0.
Nope.
velocities.
Velocity in what direction is 0? I haven't defined my directions. Perhaps that's why you're stunned at the question. It's not going up, it's not going down. That's what defines the top. So let's figure out the time it takes to get here and the time it then takes to get down again. Okay, so we do this in 2 parts. Are you ready?
Wait, we need time? I don't know how to find time.
Could you find time? This says the final velocity in the y direction equals 0. At this moment right here, there is no velocity up and there is no velocity down. What are we doing? We're finding time? How long does it take to get to a final velocity of y? 0.
I meant like the whole thing.
How you gonna do that?
I just have it.
Okay.
I don't know like how I derived it.
That's not helpful.
I just remembered it.
Shoot.
Sorry.
I need time to get to the top. I think that all of this is within your capabilities right now. Tell me the time to get to the top. If you're not looking at the 3 kinematics equations, then you're not going to be able to do it. There's a tail of 2 squares, and there's some 2 other things.
Is the first one?
The
The
clash.
initial over.
The classics?
Well,
This has final velocity in
no,
it. The
I'm
classic's
saying
not going to
if
help.
that's the final, and
Wouldn't
then
that-
isn't this
Yeah,
the
the one.
initial, like that in the y direction? Like if we
Yeah.
if we
This will be the initial in the y direction. Do you have this
resolve
value?
the vector, I don't.
Oh,
But,
shucks, neither do I.
That's the initial, and then the final 0, and then the acceleration's 9.8.
Okay, so what equation are you going to use?
V final equals V naught plus AT.
V final equals V initial plus acceleration times time. In the y direction, in the y direction, in the y direction. Good, find the time. Time to get to right here.
It's V naught over A.
V naught over A. Is it really?
Yeah. Wow. There's like negative.
It's negative
but
V
over,
naught
So it's kind of,
over A. Like that?
yeah.
That's T. That's T to get from here to here. All right, I need that time. I see that none of you are reaching for a calculator. So,
Really confused.
oh, super. Great. And then we're gonna have to do the next phase pretty soon. We can do that in orange.
Ooh, no.
Ooh, there's a blue. Blue or orange? Do you have the time? What is it?
Wait.
It's a Green Day song about that.
0.78.
Yeah.
0.78 seconds? That's your time?
Yes.
Okay, I'm really deeply afraid that you used 7.61 meters per second.
Oh man, we gotta resolve.
Oh.
Welcome back to Kinematics, guys. You all have to be good on this in a month. Let's go.
It's a good thing we're doing this. Yeah.
Yep. I'm just gonna say it, Ben. It's not gonna fix itself. Why aren't you doing it?
I don't know what to do.
Really? You don't know how to find the sides of a triangle?
Says 8:25.
Hmm?
Okay.
What's this time? You know the time?
0.32.
0.32 seconds. We have a new time coming in at 0.32 seconds. Now, how long does it take to go from the tip top to the ground?
I think you did it again.
What equation am I going to use?
Use the same one.
Same equation. You suggesting you know the initial velocity in the y direction or the final velocity in the y direction?
Don't you know both?
I do not know the final.
In the
It's
What
not
direction?
0.
I don't know the final velocity in the y direction here. Because that is just as it's hitting the ground. I don't know how fast it's going. Looking at those three kinematic equations, trying to figure out what we could do here.
I have a guess, but I couldn't tell you how I got there. Kinematics.
You had another way to do the whole thing too, sure.
Yeah.
Uh-huh. What do we know? Up at the top, what do we know?
Oh, can
The
you use
initial
the,
will be
now you
zero.
can use Taylor two squares.
Tail of two squares. The initial velocity in the y direction, in the y direction is known, and the final velocity in the y direction is not known, and delta y is not known. So
Why
you can't do
isn't
that.
it 3? Oh no, it's not.
Oh, it went up.
I know.
But how far?
Oh shit.
Could you find it?
Probably.
Let's do that.
I don't remember how to do that.
How to find how far something has gone?
You're supposed to do this in 17.
Absolutely.
Oh,
Can you repeat
The question right now is, I need to know how long it takes to go from here down to the ground. And I think that an intermediate step might be figuring out how high it is up above the ground at that moment. Then I could just say, oh, it's falling.
You just find delta y, but with the little mini.
Over here?
Yeah.
Yeah, let's find delta y for that mini. We'll do it in red. Trying to find delta y. This delta y right there, we'll call it delta y1 right there. How do we find delta y1?
Can you use Taylor squares for that too?
I know the acceleration in the y direction and the initial velocity. Totally could. All right, good. So I would get delta y equals, what am I going to get? V final in the y direction square minus v initial in the y direction square divided by 2 times the acceleration in the y direction?
Yes.
All right, what do you get? Ooh, sorry. I actually hit a kid with a marker. This has never happened before. Honestly, it's never happened before. Well, we're just waiting here. You might want to put it on 2 times speed because everyone is staring at me, hoping that I'll give them the answer. Except for Hillary.
I accidentally pressed clear. I meant to press revive.
Oh no! Oh no!
Are you gonna cut these pauses out?
Nope.
Oh man.
And then I'm going to pan the camera around and get each of your faces on there forever. And the internet will know.
Okay, I got
Oh, thanks.
0.16 meters.
0.16 meters. How about that? Is that reasonable?
Yeah.
Yeah.
Is anyone going to check that?
Yeah.
She's gonna work through that again. We could just wait.
Oh shoot. God.
Once upon a time, there was a giant who was climbing a hill to eat everybody who lived in the village over here. Can you type faster?
Stop. Okay.
The giant saw that.
0.53 meters.
Oh, well, that's totally different. Does that sound reasonable?
Yeah.
You guys are pretty agreeable. Everything's reasonable, whatever. Just as long as it saves you from having to do the problem. By the way, if you are not in America at this time, these are the people whose jobs you will be taking.
I'm gonna be an English teacher.
Wow.
Okay, an English teacher.
Oh my gosh.
In another country. Someone will want to learn English still, at least to read our literature.
Be a Chinese teacher.
Okay, good. So, where are we going right now? What's this next step? What are we doing? What the heck is going
Oh, now we
on?
have delta y.
We have delta y total?
So we can
Are you
do
talking
that.
about delta y
Yeah,
total?
so now we
Delta
can
y now from this point on, I'm going to call this delta y2. What's that?
3.53.
You're talking about negative
Negative
3.53 meters, and now it's going down. See, that's this distance right here, negative 3.53 meters. Now, this question is, if I drop a frozen chicken from 3.53 meters above the ground, how long does it take to hit the ground? Then I will take that time and add it to that time, and pretty soon we'll be able to find out how far this ball has gone. What?
I don't know.
Do you have an equation that will help us find out how long it takes to hit the ground
Yeah.
from 3.53 meters up?
Yeah.
I wish I won.
Square root 2 delta y over a.
Whoa, where did that come from?
I've already said I don't know
It's
where
a
it comes
tail of 2
from. Yeah, it's from right
squared. Wait, is that time?
Mhm.
It's not a tail of 2 squares. It's the classic then. I'll put it over here. Delta y equals, well, the initial velocity in the y direction plus 1/2 times time, plus 1/2 the acceleration in the y direction times time squared, right? Then we can solve that for time.
Wait.
I just wrote down the classic right here.
Oh.
I'm gonna You sure?
Yeah.
All right. I'm just gonna circle this and say it's 0. Why am I saying it's 0, Ben? What, Ben?
I don't know.
Ben, this is being filmed.
Can you stop saying my name?
Sure. Sir? Why is that 0?
I don't know. I feel nervous.
It says right there that the initial velocity in the y direction is 0.
That's
That's
fine,
the
then.
final one was coming up. It's the final. Sorry, it's the initial one that's coming up. I'm not gonna edit that out. That was really exciting. Sir, are you still paying attention?
Yep.
It's the final on the way up, it's the initial on the way down.
Yes.
All right, great. So of course it's 0. I'm gonna solve this for time. Time equals the square root of 2 delta y over a y. Did you already do that problem?
Me?
I was counting on you. No? You haven't done it?
I was distracted.
Oh shoot. Did you do it? Oh, dang it. Have you done this?
No.
Wow. Did you do it?
What?
All the jobs are over here. Come on over.
Is that it?
We've got it. We're gonna need people to build robots for us.
Is that what you mean?
Is that the right time?
Yeah.
Oh yeah, sure. What the heck is that 3.53?
Oh my god.
Delta y.
Oh, super. So I'm gonna plug this in right here. This time is 0.848 seconds. Is that reasonable?
Yes.
Is it?
Yeah. Because. Yeah.
Okay. Yeah, sure. Might as well be. So I'm gonna take that time and add to that time right there. Why not? That's the total time in the air, isn't it?
That's the total time.
This isn't the total time in the air. This is the time in the green part.
Oh, fine.
And then I got the time here in the
Yeah.
red part, and I need to add the red and the green together. So the total time in the air, whoa, we gotta switch to blue. This paper's getting kind of crowded, huh, Travis? Good night, Travis.
Good night.
T total is, oh shoot, am I gonna have to add this in my head?
88.88.
What? Is that 0.88?
Dang it.
Did you put another 0 in there or something? It's gonna be 1 point something.
1.173.
1.173.
6'8".
1.168? All right, great. We'll do whatever, sure. Is that the time that it takes for it to go from here to the freaking ground?
Yes.
All right, what are we gonna do with that? What was the point of all this time
Find
calculation?
delta x.
Delta X. Delta X. Could I use the classic? What's the acceleration in the X direction?
0.
0. There is no acceleration in the X direction? Is that what you're saying?
Yeah.
Super. So I'm just gonna write down the initial velocity in the X direction times time. What's the initial velocity in the X direction? Do you know it?
7.61.
No, it's not 7.61.
Oh,
6 point what?
9.
6 point. How many sig figs do you honestly have? 6.90 meters per second. I'm supposed to multiply that by 1.168 seconds. What's that total distance?
8.06.
8.1.
said-
I think that was America. Okay,
Thanks,
you ready for the next problem?
Oh, shit.
I have a
Cause
I don't know.
sure. Which color do you want to ask me about?
Couldn't you just use momentum? Like conservation of momentum to find V final and then put it into that?
Could I?
I don't know. Is that what you got here?
I do not see a way to do that.
How could you do that?
Did you try it?
Okay.
No, because like MV initial and then solve for MV final.
The problem is that you don't know which direction the velocity is because it's changing direction continuously. The momentum of the ball is not conserved because there's a net force acting on it. So we can't say that there's no momentum change. That's an interesting strategy. Once we found the time, it was easy, right? And all of this nonsense was to find the time, and I think that you guys will have an opportunity to do some more problems in kinematics. You should do more problems in kinematics. Okay, so you ready for the next problem? Or are there more questions? I will take questions. I'm happy for questions. No? Onward!
Did you have to do all of that?
No, you want to see an easier way to do it?
Yes.
Yes.
Yeah.
Do you really? Okay, here's the ball, right? And the things we know include delta y, and we are trying to find delta x, and we're going to do it by getting the time. We're still going to say the initial velocity in the x direction times the time, because there's no acceleration in the x direction. So in order to get the time, I can set up an equation that says delta y equals, well, the initial velocity in the y direction times time, plus 1/2 the acceleration in the y direction times time squared. What do I know in that equation?
V naught.
Okay, I know the initial velocity in the y direction. What else? I know the acceleration in the y direction. Anybody know 1/2? Sure, I do. Do you know delta y? Cool. What do you have? Delta y is -3 meters. For the ball's whole adventure. It's going to start here. Ooh, tropical violet. It's going to start here and do that. So I know that the delta y is -3 meters.
So you just solve for T.
Yeah, but there are 2 of them. Does that stress you out?
Yeah, a lot.
Yeah.
No.
Okay, right. What do you do? What do you do?
Pull out a T.
Pull out a t. You can't pull out a t. You'll have a 1/t over there.
Well, you
Say it.
Factor.
Factor the t?
Oh, or no, you.
You can't?
Yeah. Yeah. You, like,
It's not going to help.
Oil.
quadratic equation.
Quadratic equation. If in 7th grade you learned a little song for the quadratic equation and remember how to use it, then the problem is very easy to solve.
I learned that
But I find that
7th
most of
grade.
my juniors have forgotten it.
X
I know.
equals -b. Also my square.
Yes. For the internet! Finish it! For the internet!
No.
Oh, shucks. All right. So, what? I'm not going to teach you how to use the quadratic.
I'm not asking how to use that, but never mind.
What are you asking?
It doesn't matter.
Are you certain that you have no questions at this time?
100% positive.
I want to do the next question. It says, oh, this is really good. It says, suppose instead that the ball, and so the initial situation was the ball goes, oh my gosh. The initial situation was that the ball goes up the ramp and, dang it. And it rolls without sticking. Rolling without sticking, rolling without slipping here. And in this situation, there's no friction on the ramp. None. Super slick ramp. So we've got friction here because it's rolling without slipping. Friction there. Friction there. This was our launch that we just considered, where it's rolling without slipping. But if there's no friction at all, and I'm gonna let our viewers have a little moment to think about this. Almost everyone who read this problem answered it wrong. The problem when you're about to pause is you need to find a way out of it, so I'll give us a play button that we can press in just a moment.
Aren't you gonna remind him to actually pause?
Pause the video, jerk. Think you can just let me solve all your problems for you? Huh? Sitting back there like some kind of American? No, oh, the teacher will get it, that's fine. Yeah. Yeah?
How is energy conserved if there's friction?
That's what I'm talking about. Energy is still conserved even though there's friction because it's static friction.
How is it not kinetic friction?
It's not kinetic friction because the bottom of the wheel is never moving. Great question. The bottom of the wheel never moves relative to the ground unless there's this situation. Don't worry, it's not going to steal any energy because there's still no friction. There's no kinetic friction either in such a case. But this sucker is spinning. Can you imagine it spinning? How is omega going to change for this guy? It comes in here with an omega naught, and up here it's got an omega final. What do you think about omega final and omega naught for situation 2 when the ball is up here and it's been rolling up the ramp with no friction?
It's gonna be less.
What's going to be less? You mean omega is going to have decreased from this situation here?
Yeah.
I don't think so. Only friction can make it change,
What
right?
about like M?
So it's equal to?
potential-
They're equal.
What?
I am not saying what you think I just said. I'm not saying that these are going the same speed. I'm saying, here's my question right now. I'm saying, oh, should we play? I'm saying that omega here is the same as omega here because this ball has experienced no torque as it goes up the ramp.
But it's when something get bigger.
What's going to get bigger?
Oh no, when. You're right.
Isn't that crazy?
What?
Isn't that insane? Well, I'm going to zoom into the ball for just a moment. Now, here we've got the ball, and the forces that act on it include mg acting straight down, and the normal force acting straight out, right? Those are the two forces that act on the ball if there's no friction. Both of those are acting on the center of mass, and so they produce no torque. So the ball does not slow its rotation and it does not increase its rotation. Whatever energy it had trapped up in rotation here is also trapped up in rotation there. Guess what? That's 500 joules worth. 500 joules. 500 joules. Rotational kinetic energy. K rotational equals 500 joules. K rotational equals 500 joules. Is that okay with you?
Wait, but the question asks about speed.
Mm-hmm. I'm about ready to talk about
Okay,
speed right
I
now. Do
just
you want to talk about speed now?
I was just making sure you knew that.
Absolutely.
Okay.
Where does the energy come from to climb up this hill? Whoa! Let's not even do that. I refuse to talk about speed yet. Green line. Are you okay, sir?
Yep.
Great. I want to talk about this right now. Is there a torque on this ball?
Doesn't there have to be an excess of Oh, is that the middle?
It's the middle of the ball. Good question.
Then yeah. because
Yeah, there
it's-
totally is. There totally is. Do you think, as it rolls, that it has slowed down while it went up the hill? Did this one slow down as it went up the hill?
No.
What? Sure did. The rotation didn't slow down, but the ball slowed down, right? This one also slows down as it rolls up the hill. But remember, in this one, since we have rolling without slipping, we've got the condition that Vt equals omega times Ra. And do you believe that it's going slower here than it was here?
Yeah.
Then you must also believe that either Ra or omega has gotten smaller. Do you think the radius of the ball will shrink as it rolls up the hill? That would be some kind of ball. I would buy one for my children. Does it get bigger when it rolls back downhill? Wow. What's actually happening?
Omega's getting
Omega's
It's
getting
just
smaller.
rotating.
It's rotating less. Sure. This one is rotating less. If I were looking at omega final right here and omega initial right here, I would be able to make the statement that omega final is less than omega initial. But down here in the purple, was it purple or was it tropical violet? I think it might have been tropical violet, was it? Oh yeah, it totally was. Down here I could make the statement that omega final equals omega initial. And then it would probably beneath it say, whoa. What does this mean though?
And
Anecdote?
It slowed down.
It slowed down. But wait a second. Didn't this one also slow down to get to the top?
Yeah.
What? I thought. it
yeah,
didn't.
so then how?
Right?
Sorry.
Question. There was 500 joules right here. That is K rotational at the beginning, 500 joules. What about K rotational up at the top? What is it? Sorry?
Wouldn't it have to be the same?
No. Because K rotational has to do with I and it has to do with omega, right?
So
1 half I
that's
omega
the
squared.
same.
Isn't it just less than 500 joules? Isn't it less? Let's just call it less. Isn't it less?
Why?
Go. Why is it less?
Does that equation says it will because there's like gravity and it's telling you
Because
to not
W-
go up the hill.
Because omega gets less.
And omega. Oh, friction.
Omega gets less. Friction. Lots of words thrown out here. I love it. I like the statement that omega becomes less on this hill. You know why omega becomes less? Because it slows down. But it slows down on this hill too. The ball is not moving as fast as it goes up the hill in this case, and it's not moving as fast when it goes up the hill in this case. But we are reminded, thank you, that the purpose of this question is to figure out in which of these situations will the ball launch out with the greater velocity? Pew, pew, which one? Are you ready to put everything together at this time? Okay, go.
No.
Oh, somebody else? Maybe someone else will do it. Will you do it?
Well, I just have a question. So, like, in the second example, okay, in the first one, it's rolling without slipping, so that means that it has kinetic energy from translational and rotational. In the bottom one, does it, I don't know if this is, like, connected at all, but does the bottom one have kinetic energy from rotational?
Yeah,
Okay, so then I don't know.
it does. In fact, it still has 500 joules trapped up in the rotational energy.
Okay.
But this one doesn't have 500 joules trapped up in the rotational energy.
But wouldn't this
So
one
then
be
the bottom one would be going faster? No, I don't know. Never mind.
That's what I was
What
gonna
did you say? Oh,
I was gonna say that. Because the velocity on top would have to decrease. Oh wait, they both. Never mind. Never mind.
How if omega like you can't use that equation at the bottom? Because if omega
I-
stays the same
you're
and the
right.
radius stays the same, then that would say
Right.
velocity stays
So
the
this equation is a
That's
rolling
not
without
true.
slipping equation. And so we can only use it up top. We can't
Okay.
use it down at the bottom.
Okay.
At the bottom, we actually have more information, it seems to me, because I know that exactly all of the energy is still trapped up in the rotation. Oh shoot, looks like the battery's dying. kinetic energy. So I'm thinking that mi is mf. If I say that initial mechanical energy is final mechanical energy, then I could write down all the forms of energy that are present initially. Initially, I've got, we just did that, 1,750 joules. And that's kinetic rotational and kinetic translational. Now, what about the final the final mechanical energy? Well, it's got mgh, and the h is 3 meters up. Most of my students stopped right there, and then they said, wait, this is that whole form, the 1/2 mv squared times in parentheses 1 plus 2/5, and then they solved it for v. That's a disaster, because this is not the final energy. If you don't write any kinetic energy term right here, then you're already telling me that you think it's stopped. It's rotational. That's cool. So 2/7 of the total energy is rotational, and the other 5/7 must be translational. So that's cool. If you actually plug in the numbers right here, you find that this is 1,250 joules plus 500 J's. Okay, cool. So, all right, great. Then the next part of the problem says, what is the speed of the sphere as it leaves the top? And I had people do this in all sorts of crazy ways, but I'm gonna ask you to approach this, by thinking about what's true at the end. That's pretty lame instruction, right? What is true at the end? Well, at the end, the sphere is up here, and it has gained potential energy, and it has lost, get into there also. Here I go. 1/2 2/5 m r square, capital R, lowercase r, well, let's just use a capital R right there. And then instead of omega square, I'm gonna write v square over r square. Some stuff cancels. And on the next line, r square, r square. So, this is so cool. Look, it says 1/2 mv square plus 1/2 mv square multiplied by 2/5. That's pretty awesome. What if I just factor out the 1/2 mv square and say 1 plus 2/5? This is a form that my students in class have seen pretty often, and it helps you to find out the fraction of the energy that is translational and the fraction of the energy that is. So let's start doing this problem. The first part, it says, what is the total kinetic energy of the sphere as it rolls along the horizontal surface? So I'm just gonna note that there are two forms of kinetic energy. I'm gonna say we've got ourselves K translational and we've got ourselves K rotational. And those take the two forms 1/2 mv square plus 1/2 I omega square. It is rolling without slipping, so we can further develop this by saying, I'm just gonna write the 1/2 mv square again. But then I note that omega, by the way, omega is v divided by r. This is true when we have rolling without slipping situation, and we've totally got that here. So I'm gonna plug that into there, and I've got, oh shoot, why don't I take this moment of inertia and plug. So I got this old physics problem, and it's a really wonderful problem. There's a sphere, see? And the sphere has a moment of inertia of 2/5 mr square, so I guess it's a solid sphere, right? That's what they do. It's got a mass of 25 kilograms, got a radius of 0.2 meters. This is a dense little sucker, maybe it's made out of metal, and it's gonna be rolling up this ramp right here. And it says that it rolls up the incline without slipping, and it also says that it's not gonna change its velocity while it's going along here. So I'm gonna draw little bumpies to show that there's friction all along this section right here. But remember, it's always static friction, so it's not going to be slowing down here. And when it's going up the ramp, it's not going to be losing kinetic energy to heat, it's only gonna be losing kinetic energy to potential energy.